Hello guys, today in this video we are going to discuss about Doppler effect. Okay, so what is Doppler effect? So Doppler effect is actually the change in frequency, right? When sound producing or any wave emitting source actually approaches to the observer or it goes away from the observer. What is the change in the original frequency of the sound or original frequency of the light or the original frequency of the disturbance that is produced from the source? Okay, so Doppler effect gives you the idea about that change, right? So here you can see in the first diagram here, suppose you can see the bug here at the center, right, producing disturbances in water, right, and you can see the disturbance is getting propagated in all directions, right? So considering this bug is to be the point of wave producing source, right? So here you can see you can see the ripples that is formed on the surface of water, and these ripples represent the wavefront, right? So the distance between the consecutive wavefront, as we know, gives you the lambda, right, the wavelength of the disturbance, right? So same here also you can see for A, the observer which is at A, you can see this is also lambda, right, for a stationary bug producing disturbance in water, right? So if we will see that the bug is moving forward and towards the observer B, right, and away from the observer A, then you can see there is a change in the distance between these consecutive wavefronts, right? So here what we said, the disturbance is having a wavelength lambda. So V is equal to F lambda for this one, if you write, where V is what? V is the speed of propagation of the disturbance, F is the frequency, and lambda is the wavelength, right? Now here, as the bug starts moving, it will move with a speed, with a velocity, as it is moving with a velocity. Let us take it as Vs, that is the source speed of the source, and it's moving towards B, and you can see it's going away from A, the point A, right? Now you can see that there is the distance between these consecutive wavefronts here, you can see, is increasing, right? And here the wavefronts, you can see that the wavefronts are getting squeezed, like, no, where not wavefronts are getting squeezed, the distance between the wavefronts, consecutive wavefronts, are reduced, right? So now why this happens? Okay, we need to find out this change in lambda dash and lambda double dash to see what is the change in the frequency. So frequency for this observer, the observer from which the source of that disturbance is going away, and for the observer B, for whom the source is actually coming or approaching towards the observer, right? So what will happen to the frequency? Now here you can see this is just the same diagram. Here you can see, so this is our lambda prime, and this distance, small distance, you can see is lambda double prime or double dash, right? So for now, I mean, if I'll write this one, so V is equal to, so there will be change in frequency. Let us say for this observer A we are writing, so velocity will be F dash multiplied with lambda dash. This way we can write. For observer V, we can write V is equal to F double dash and lambda double dash, because we said that we change in wavelength, then there will be a change in frequency. So we can write this way: V is equal to F double dash lambda double dash. So this V is what? The speed of the disturbance, which is same, right? Whatever change you are getting is because of the movement of the source, right? So that is considered to be Vs, right? So using this, we can frame a mathematical model to find out the changed frequency, right? And I mean, for the observer A and for the observer B. Okay, so how to do that? So as I said, let us start with this. Okay, V is equal to F dash lambda dash and V is equal to F double dash lambda dash. This is for B and this is for A, right? Then the second thing is, as I said, for observer B, you can see the source is moving here, okay, in this direction for the observer B, right? At the same time, the disturbance is also moving in the same direction, okay, with our speed V, right? So if you want to find out the relative speed here, as they are directed in the same direction in the same time t, for example, okay, the relative velocity here will be v minus vs. This will be the relative velocity. Now for observer A, if you will see, source is going away from this with a speed Vs, but the disturbance is moving in this direction, approach, like, the disturbance is moving in this direction with speed V. So the relative velocity for this one will be V plus Vs. So this is what is important, and we need to understand this. V plus Vs for observer A and V minus Vs for the observer V. Okay, let us now write the value of lambda. So lambda here, if I write what is lambda double dash in terms of frequency, we know that V is equal to F lambda, so lambda is equal to V by F, right? So V by F here, so we can substitute what is the relative velocity here. Relative velocity is your V minus Vs, right? This is what we got, the velocity for the observer B, and lambda is equal to V by F, so we got the frequency. Frequency is what? Frequency is your F. Okay, the same way you can write here lambda dash is equal to V plus Vs, okay, into T, that is 1 by F, right? So that is frequency for the same time T, right? Time is T. So here, so once you got this value, lambda dash is equal to V by V plus Vs divided by F, and lambda double dash is equal to this, then you can write in terms of, like, in terms of original frequency and this. So what is this lambda double dash? Lambda double dash here from this equation, we said lambda double dash is equal, in terms of the changed frequency, if I'll write. So lambda double dash gives us V divided by F double dash, right? And similarly here you can write lambda dash is equal to V divided by F dash. Substitute, okay? So here I will write lambda double dash is V divided by F double dash, okay? That is equal to V minus Vs divided by F. This is what we got, okay? You cross multiply and then you write the value. So if you want to write F double dash only, then you can write F double dash into V minus Vs into V minus Vs is equal to V times F, right? So you can write F double dash is equal to V divided by V minus Vs times F. Okay, so we got F double dash is equal to V minus Vs divided by F. Now you see, for any value of Vs, any non-zero value of Vs, that is the source, or here the bug, okay, the speed of the bug, okay, you can see V minus Vs here in the denominator is less than the numerator here. So you can see that, F double dash will always be what? Greater than F, because you can see this V minus Vs will be less than V, right? So we can write V divided by V minus Vs will be always what? Less than V divided by V minus S will be greater than 1. So you multiply this F here. So you can see, F double dash is equal to something like, this V minus Vs, it is given V divided by V minus Vs times F. So it is greater than 1, and here you multiplied with F. So we can write that F double dash is always greater than F, right? F double dash is greater than F. So for the source here at B, if the disturbance is approaching to B, then its frequency increases, okay? Its frequency increases. So here we got by what amount, you can see V divided by V minus Vs times F. Okay, so original frequency is F, now it is increased by this ratio V divided by V minus Vs, right? The same way you can do it for the source A. So source A, we got lambda dash is equal to V by F dash. So if I'll substitute here, V by F dash is equal to V plus Vs divided by F, right? So you can write what is F dash. So F dash will be what? V divided by V plus Vs times F. So now here, if you'll see, F dash is equal to V divided by V plus Vs. This V plus Vs is greater than V. So V by V plus Vs will be less than 1. So here you can see F dash will be what? Less than F. So the frequency that reaches here at A is less than the frequency that is produced by the source if it is going away from the observer A. Okay, so this is what we said. This is the Doppler effect. You can see the changed frequency, right, in both the cases. Now, that's, you can take a real example. For example, the siren of an ambulance or something. Then when the ambulance approaches us, it seems like the frequency is more, right? And as it goes away, it crosses you and goes away from you, then it fades, right? The frequency decreases. So this can be explained by using this simple mathematical explanation, right? Further, if you want to understand what is a sonic boom, if you have heard about this, sonic boom. Let us try to understand it qualitatively. So what happens here, you can see I have shown you a jet, right? Or airplane flying. Now here, suppose this is the source. Here you can see that S is written, okay? The front of the jet is shown, right? And this jet is producing a noise or sound, right? Okay, so here at the same time the jet is moving, right? So here the plane is moving, right? At the same time the sound that it creates is also moving in the same direction. You can see that, right? So if you go back to the previous diagram, here you can see, right, that lambda double dash, right, will be what here is almost, I mean zero, when the speed, here you can see the speed v matches with the Vs. V matches with Vs. V is nearly equal to Vs. That means, suppose for a airplane, V is the sound that is produced by the plane, and Vs is the speed of the plane, right? When they will match, then this lambda dash will not exist. You can see they will all these crests will be piled up at the same point B here, okay, which is shown here at this point. You can see. So this is the point where all the crests, okay, the wavefronts, the crest will be, piled up over here, right? And then it will create a sound barrier. So all crests piled up means what? So these crests actually, in terms of pressure, if you will see for a sound wave moving in air medium, right? The pressure is high in the crest, and when all these crests they pile up, the pressure is huge there, right? At this particular point, and this creates a sound barrier. So we call it a sound barrier. Okay, now when the plane exceeds, okay, that speed of the sound, right, when we said supersonic, right, speed exceeds the speed of the sound, okay, then it has to overcome this barrier that is created over here, sound barrier. And here the air pressure is huge, and hence the resistance offered by these air molecules to this plane is huge, and the plane has to overcome that potential, like, the pressure barrier, right? So it creates a huge noise or sound, okay, and we call that a sonic boom. So here is a clip for you, like, if you want to uh, if you have not experienced the sound, a sonic boom, then you can just, I'm just playing it, you can hear it.